This will be problem set 2 for the FE exam review. So we will start with a gas dechlorination problem looking at sulfur dioxide that's typically used to dechlorinate any residual chlorine that would be embedded into a system. And so we've got, let's see here, let's read the problem statement here. So we've got sulfur dioxide is added, water treatment facility required, and so it has 2.5 milligrams per liter of excess chlorine. So how many 100-pound canisters of sulfur dioxide will be required on a weekly basis? So we've got a lot of units to work with here for a daily water treatment flow of 10 million gallons per day, assuming 1 milligram per liter sulfur dioxide is required for every 1 milligram per liter of excess chlorine. So first we attack this by looking at the chlorine demand, convert to liters to gallon, so gallons per day, 7 days. Weekly, this would be 7 days. Milligrams per kilogram, kilogram to pounds. Each canister is 100 pounds. Because we have that was given as 100-pound canister, and then our conversion right here. So for every 1 milligram of chlorine, on the bottom here is our Cl2. We need this much sulfur dioxide, and so that would result in about 14.58 canisters, or 15 canisters. The answer would be B. Assuming that the same excess chlorine residual is to be treated with sodium sulfite instead of SO2, how many 1,000 pound canisters of sodium sulfite will be required on a monthly basis? Oh geez, so just more units conversions that we have on here. So we would take our 2.5 milligrams per liter, and then we have this. So we have this relationship of chlorine to sodium sulfite, convert gallons to liters, flow rate 30-day, this would be on a monthly basis, milligrams to kilograms, kilograms to pounds, and then the number of canisters that would be provided or required, and we get 11.25 or 12 canisters, this round up, so they don't sell these in half canisters. Okay, balance the following equations. So we have to think back to our chemistry class and see how we would perform this balance. So we're going to balance. Let's start with our hydrogens here. So we've got So we got 6 here. So it looks like we're going to need 3 on this one to balance that. Then we can move to our carbons. So we've got 1, 2, and so we'll need 2 here, and then we can finish up with our oxygen. So we've got, this looks like that would be 1. So we can do, let's just see, we've got 1. So on this side we've got 3, 7, 1. So it looks like this would be 3 on this. So how many water molecules? The answer would be 3 with D. So go back and refer to your chemistry textbook, maybe the Intro to Environmental class, where you had some practice balancing some equations. All right, determine the mass of ethanol so ethanol, C2H6O in a 12 ounce. All right, so we've got ounces converted to liters, assuming the beer contains 1% ethanol. Some more units, pretty simple. So we got a 12 ounce beer, convert that to ounces. Ounces to liters. 1 liter of beer is 0. This would be our 1% by concentration, or by mass, I guess that would be in there. So 1 liter ethanol is 1 kilogram of ethanol, assuming that it's close to the unit weight of water. And then 1 kilogram of ethanol is 10 to the 6 milligrams. And so we have 3,550 milligrams of ethanol that would be in there. So the answer would be C. The next problem, and this looks like something that could happen in your dorm room, although you're not allowed to have these beverages in your dorm room. Your roommate accidentally drops a 12-ounce beer from the previous problem, contains 1% ethanol, into your 200-gallon fish tank. Oh my, assume the DO initial is, we're almost at saturation or beyond saturation, 10 milligrams per liter. The tank is sealed to the atmosphere. The theoretical oxygen demand for this ethanol is 2.09 milligrams of oxygen per milligram of ethanol. So that's how much is consumed given this relationship. So this is not in your, let's say, not in your equation FE exam, but you can still use this equation. How much is the final concentration of dissolved oxygen in your fish tank based upon this, essentially the theoretical oxygen demand of ethanol? So we've got this relationship that's provided from the problem statement, and we need to calculate the DO final inside of this problem. And so the DO final is going to be equal to, if we can solve this and set up our units proportionally, so our DO initial 10 milligrams per liter minus, and so we have this many milligrams of ethanol is in the system, and this is how much oxygen is consumed per milligram of ethanol. All that divided by our 200 gallons and converting that to liters. And so if we did that, we would have 0.19 milligrams of O2 per liter would be the final concentration, assuming we're at equilibrium or steady state in this problem. So the fish would most likely not survive this catastrophic event. Our last problem is looking at the wastewater sewage decay in a stream as a decay rate K1 of 0.2 per day, and determine the half-life. And so this is using reaction rate coefficients or constants. And this equation would be provided in your FE exam reference formula manual. And so what is the half-life? How long does it take for half of it to degrade? And so one clear and easy assumption is that 0.5 C naught is equal to C naught. So we're calculating the half-life of this. What's the half the initial C naught concentration? And so this can be simplified as we've gone over in our intro to environmental class. T1 half is equal to the natural log 2 divided by K1. But even if you didn't know this equation here, you could certainly solve it here by just putting in 0.5 C naught for the CF, the final concentration, and putting in the appropriate values. So we have this K1 is given, and we would solve for the T, the time. And when we put that in, we would get 3.5, which is closer to 4. Well, this one's pretty, I would probably say D, since it's closer to 4.0 versus 2.5 per day, but it looks like this manual says it's C, but I would go with the one that's actually closer at 4.0 per day. So again, this is the conclusion of the review of some basic environmental principles or processes. Go back and review your 326 notes, be familiar with a lot of the formulas, especially BOD, COD, problems like that we've gone over in this review, and just be well rested and ready to solve problems and know where all the appropriate equations would be. So I'd recommend going back and solving these problems on your own and just become proficient and fast, let's say, at solving these types of problems.